Once you couple these massless, quote, massless fermions to a vector gauge field, in this case, the electromagnetic field, it opens this channel for decay that is 300 million times faster than the charged cases, which have to decay by going to muons and to leptons, muons and neutrinos. And so this is a very famous Adler-Bell-Jaquet anomaly. And actually, the calculation came very close to accounting for 300 million, except it was short by a factor of 9. And this was the earliest indication that there are 3 colors of quarks. You can read about this in a very nice article that Greenberg wrote in Physics Today. So later on, it was realized that the chiral anomaly plays a very important role as a gatekeeper. If you propose a gauge theory, it better not have any chiral anomalies in the theory. Any appearance of the chiral anomaly leads to non-conservation of what's called the axial current density and renders the theory unrenormalizable. So in the most successful gauge theory, which is the GWS theory, all these anomalies cancel pairwise right across 3 generations of quarks. This has been called magical by Peskin and Schroeder. First time I've seen the word magical in any serious physics textbook. So this is sort of the depth of the mystery of the chiral anomaly. So in 83, Nielsen and Ninomiya proposed that perhaps we could see this in a crystal. Right? And, but the caveat is that it has to be even in space-time dimensions. So when graphene was discovered, there was a flurry of excitement because now you have Dirac states in condensed matter. But then people rapidly realized that it won't go because it's 2 plus 1. Right? So it's got to be 3 plus 1 to make this a viable prospect. The Nielsen-Ninomiya prediction is as follows. I suppose you did have Dirac states in a crystal, then it would automatically have equal numbers of right movers and left movers, as Ed explained this morning, right? But the moment you apply an electric field, you would cause charge to be pumped from the left mover to the right mover. So this looked interesting from the non-condensed matter point of view because it looked like charge was appearing spontaneously on the right mover, right? And it was spontaneously disappearing from the other branch. But then if you look at it from the level of, let's say, Ashcroft and Mermin, you realize, as many people did, that, wait a minute, these bands are actually connected deep in the Fermi sea. So this is nothing but shifting of the Fermi surface, right, in an electric field, right? And this is exactly how I thought about it, and I just didn't understand why this would be even worthy of a note, because basically this is at the level of, say, what you would do in a ordinary Boltzmann type calculation. However, what I was missing, and this is what the experiment will teach us, is that we think that chirality is significant. The fact that these 2 branches have opposite chiralities. The second point is that this is steerable by a magnetic field. And this is going to be important in what I will talk about in a second. And then the notion of relaxation. How do you actually relax the current? That is also a very important issue. One way to look at the wild nodes is that if you could split them, they are the sources of Berry curvature, as Charlie explained already. So one of the wild nodes will be a source, and the other one will be a sink. And the Berry curvature is the curl in K space of the vector potential, the Berry potential. And if you could draw a Gaussian surface around, in K-space, around one of the nodes, you would get a positive number 1 for the chirality, or -1, depending on whether it's the source or the sink, right? But the calculation using the determinant of the velocity matrix is a lot easier, right? This one, you can see the calculation in the book by Bernovic. It's actually much more messy to do. So, with the realization that wild nodes could actually happen in iridates, this was the insight by Vishwanath and co-workers, there was an explosion of papers as theorists dusted off their old preprints and posted on the web. And now you can really see Newtonian physics in condensed matter. And I tried to track it in the span of 3 years. I think maybe more than 100 such postings were made. And I didn't read all of them, obviously. But it was just an explosion of theoretical interest. And a year later, experimentalists started to work on this problem. So again, to repeat what Ed already covered, when you have massless Dirac fermions, they split naturally into right and left-handed populations, right? And the two don't really talk to each other. They are separately conserved, and that's what we mean by chiral symmetry. You can break that chiral symmetry by reinstating mass, but that's obviously not the way to go. But if you apply an electromagnetic coupling to electromagnetic fields, then you also break the chiral symmetry. That breaking is the charge pumping that I mentioned before. So many of these groups propose that if you did go to the lowest Landau level, and here I'm drawing the two wild nodes that were superposed, slightly displaced for clarity, then you see that one of them will have a right-moving Landau level, right, in the quantum limit, whereas the other one will be left-moving. So you can easily derive this term which describes the pumping from one population to the other by just using the Landau level and calculating the rate at which you pick up states as you accelerate k sub z in an electric field, and that's the expression, which exactly recovers the field theory calculation. Now, you don't really need to go to the lowest Landau level. The phenomenon becomes manifest in weak fields, and this is first pointed out by Stahn and Spivak, both in the audience, and they derived this formula which shows that this enhanced conductivity that corresponds to this current goes like B squared. So we'll come back to this, but importantly, it involves the relaxation time, which relaxes this additional current. Right. So this again, we'll come back to. All right, so in this new generation of crystals, the guys in Kava's group, Kushwaha and Jason Krisen, found a way to anneal the crystals so that the amount of vacancies greatly diminished. And this allowed the Fermi energy to move much closer to the node, from 400 millivolts to 30. And Jun Xiong took this to the magnet lab and immediately found something really bizarre, right? So first of all, unlike the metallic resistivity that I showed before, that by the way is a fairly accurate drawing of what the crystals look like, he noticed that the resistivity was non-metallic. It now goes up as you cool down, but it's not really insulating, it saturates. The Hall effect has this change of sign occurring near 50 Kelvin. It has a minimum at 100 Kelvin. The surprising feature is the longitudinal magnetoresistance. So by pointing the field parallel to the current, right, that's the chiral anomaly direction, June found that the resistance dropped dramatically. And you know, the drop is precipitous. It starts at a fraction of a Tesla and just keeps going down. And you know, he's taken this to now 30 Tesla, but anyway, just showing the low field. So this is anomalous. This you never see in ordinary conductors. And the reason is, okay, so this slide surveys some textbook physics that's for the purpose of discussion. Suppose you have one band, right? Suppose you have one band, one pocket, and you want to introduce all kinds of anisotropies, which I can incorporate into an effective mass that's different along 3 directions. Then you can carry out the Boltzmann transport, that's the equation. Right? This is what you will see in Simon, for example. You can easily solve this in what's called the relaxation approximation. And this is the resistivity tensor. It is as simple as you can imagine getting. Right? There's no field dependence except in the off-diagonal terms. That's the Hall effect. And look at the diagonal elements. It's independent of magnetic field, but of course anisotropic, right? It picks up the effective mass anisotropy. So if you monitor the row 1, which is the longitudinal, for example, you would see absolutely no magnetic resistance. So this is the fact that all transport folks know, that a single band semiconductor or semi-metal, it's extremely hard to see magnetic resistance. And not only that, on top of that, you want to see negative, right? Negative MR is even rarer. Some checks to make sure that we know what we are doing. We can see quantum oscillations, but now because of the very tiny pocket and the restricted mean free path, remember we're not getting very close to no, you see at most 3. Right? And nonetheless, they are enough to allow us to get the slope when you do this index plot. And that's all we need, because that slope tells us the size of the Fermi surface pocket. Right? And it agrees very well with the density inferred from the Hall effect. The oscillations, even though they are small, right, and there are only a few, they are quite robust. So this shows different ways of removing the background. You can see that changes the amplitude, but not the position. The position is more or less barely shifted by this different subtraction. So we're pretty confident that the pocket we see is very tiny, and we're very close, within 30 millivolts of the node. Okay, so here's a test, right? So if you imagine, so now let's say I don't know anything about any anomaly, and I'm trying to understand what on earth could give rise to this very large current, right? Because we're seeing a factor of almost 5 to 10 drop in the resistivity. That's a big current, right? So is it something specific to the anisotropy and scattering in that direction? So a test would be to rotate the current to the perpendicular direction and then see what happens. Right? So here's the data. So it's quite busy, and let me walk you through it. In this geometry, that's the beginning. Sorry, this is starting to die too. The current is along the x-axis, right? And the field is being rotated in the plane of the crystal. So here's perhaps, sorry, this didn't come out well. The field is being rotated in the xy plane, and at every angle, the computer takes the data. So you can sort of march through this series of angles, and you see that at most angles, the MR is very large and positive. This is the background that we don't like, that we don't want. But within a few degrees of the alignment, you see a very dramatic decrease in the resistance. Right? So this is the anomalous negative MR. Now you rotate the current to be parallel to Y. And you repeat the experiment, right, without telling the computer which angle is special. And you see that exactly the same phenomenon occurs, right? So when you are very far from alignment, you see this background V-shaped magnetic resistance. But then when you come within a few degrees of the current, again, you see this enhanced current. Right? So that shows that even in weak fields, it is the magnetic field and the electric field that determines this enhanced current. So that's what we call the plume, and this plume can be steered by either the magnetic field or the electric field. Now, show some dirty laundry, right? So when experimentalists show you curves that look beautifully symmetric, what they've actually done is to symmetrize it by hand, right? And then that's an accepted procedure because you never can pick up the resistivity tensor alone, right? You always pick up the Hall effect as well because of misalignment or sample inhomogeneity. So the Hall effect is very large. Sorry. So the Hall effect is very large, but you see that at most it tilts the MR curves by maybe 10, 20 degrees. It doesn't change the pattern that we're looking for, which is this characteristic decrease for both field directions. So we felt pretty comfortable taking the symmetrized curve as indicative of the intrinsic MR. Now, how narrow is that angle? Okay, so this is a completely different set of measurements. Now, you hold the field fixed, right? And then you hold the magnitude of the field fixed, and then you step through the angle, taking very tiny steps to basically find the enhanced current. And so now I'm plotting this as a conductance enhancement. So this is now actually seeing the conductance enhancement, and that we claim is the charge pumping This we claim is the charge pumping plume that arises when the field aligns with the electric field. And you see that it just shoots up, and the width can be fitted to a cosine to the fourth theta, cosine theta to the fourth power, which is already much higher than the E dot B would lead to. Then there should be a cosine theta. But it gets worse, right? If you go to 7 Tesla, you see that's extremely narrow, right? So this is what we call the plume. That it's much narrower, it's much more exacting to get the field along a certain direction to see the current appear. So this is a mystery. Why is it so narrow? Why doesn't it just give the cos E dot B cosine theta effect? So perhaps this is a challenge that theorists will undertake in the coming year. Same thing if you now rotate the field out of plane along the zx direction, and again you're doing the same measurement here. Hold the field, change the angle, and at low fields 2 Tesla, okay, it's like cosine to the fourth, but it gets really narrow. So these polar plots to show the angular spread of this plume. That's an experimental surprise, and then this shows that this is perhaps a good experiment because otherwise we'll learn nothing, right? It's got to turn up features that are not anticipated by the theory. So the last topic is the relaxation. That I think is the most difficult issue to understand. We can convert our curves to conductance versus field, and you see that it's parabolic, right? Exactly what the Son-Spivak prediction has, right? So these are weak fields. The conductance should be parabolic. Now, all these parameters are known to us. The velocity, the Fermi energy, and so on, they're all known. So we can basically pull out the relaxation time. And to our surprise, this is very long. It's 40 to 60, not quite 80. It's 40 to 60 times the Drude relaxation. Drude means 0 field, when none of these anomalies are supposed to be there. Right? So you can more or less eyeball the data and convince yourself